second, let me start with a little disclaimer. So this paper is only partly about capital mobility and international competition. It also relates to the topics of this morning, in particular the tax interaction effect, and it adds what I think are some interesting dimensions. So let me first give you a very basic motivation. So this is a paper about optimal taxation. So it basically starts from the question, assuming that a government wants to internalize the impacts of climate change, what should be the tax that they impose on carbon emissions? So many papers have asked this question before. Okay, sorry. So further away or? Yeah, okay. So what I want to add to this, I want to basically start with 3 observations. First, as we have heard this morning, distortionary income taxation affects the government's problem, the government's environmental policy problem. This was literature which has been started by Bovenberg and de Moy, and then there were many papers more, including several of people in this very room. And I was lucky enough that Larry Golder this morning presented or gave his talk and already defined what is the tax interaction effect, the revenue recycling effect. So that saves me a bit of time. Always nice to be standing on the shoulders of giants, right? Second observation, so these studies, this literature was mainly set in a static framework. So it was more general, I would say, about environmental policy, less about climate policy. Climate change, of course, is inherently a dynamic problem. So impacts occur at a very far future. And then a third observation, what we know from mainly macro models, is that in dynamic environments where we have distortionary taxation and income taxation, what matters is, or what might matter is commitment, or rather the lack of commitment. So there might be a difference if we assume that a government can commit to future policies or cannot commit to future policies. And then I refine the question at the beginning, saying what is the optimal carbon tax in a dynamic economy, assuming that there are distortionary income taxes and the government is not able to commit. So more specifically, what do I do in this paper? So this is a paper on optimal taxation. I start with a first best climate economy model in the spirit of DICE or more recently Golosov et al. And I add the 2 features I described, distortionary income taxation. I should mention here, I assume linear taxes. So this is more a Ramsey type of problem. And I assume that there's no commitment to future tax rates. Let me very briefly talk why this matters. So we know that in the presence of distortionary income taxation, a commitment solution is not time consistent, meaning that if, let's say, a government at period 0 announces a policy for all future periods, once we get to the future, there's basically an incentive to re-optimize. So in other words, if there's no commitment device that the government has access to, whatever a government announces today for the future is in the end cheap talk. Assuming that there's no commitment, what we basically get here is then a dynamic game between successive governments. And this assumption then makes solving the model more computationally involved. So in particular, it requires using recursive methods. And on the technical side, I will focus here on Markov perfect equilibria when I solve the model. I then consider 2 settings. First, I consider a global one-region model, which I use to derive, I would say, my main analytical or main theoretical results. And then I also look at a first step towards a more realistic framework, a 2-region setting where I have unilateral climate policy making, which I here define quite simply as the absence of a global planner, or there's no policy cooperation among regions. And then the research question, so the first one I more or less ask, so how does income taxation on the lack of commitment affect optimal climate policy? If one wants to think in terms of models, one could also rephrase the question saying, assuming we have a model like DICE or like others, what would be, or how robust would prescriptions coming out of that model if we relax some key assumptions? So for example, that the commitment solution is time consistent, or that there are no distortions from fiscal policy. Third question is relative to, let's say, a hypothetical commitment device. what would that change, or what would be the difference between a commitment solution and a solution without commitment? And then in a two-region or in a more general multi-region setting, what is the effect of distortionary taxation when you have unilateral policy making? So let me very briefly talk about the model. It is in some sense a very standard model. It's deterministic infinite horizon exogenous growth model. There's a representative agent. So I know that some people here don't like representative agents, but I have one, unfortunately. I add fossil fuel or energy, I will use these terms more or less as synonyms, as a factor of production. So there's a difference to the DICE model, actually. And then I also have climate change in the forms of mean temperature change, which, as in the DICE model, affects the production process, or affects the productivity with a damage function. And I also allow for direct utility effects. Neither of them, you could also do it with only one of them, but I wanted to allow for more generality here. Moreover, there's a one-to-one mapping between fossil fuel use and carbon emissions. So I abstract from technologies like CCS, for example. And I model fossil fuel as a non-exhaustible resource, just to facilitate tractability of the model. So what I think here, the fossil fuel I'm thinking of here is more coal than oil or gas. In the interest of time, since this is a short presentation, I decided not to show you any analytical expressions. I invite you to read the paper. I spent quite a bit amount of time to characterize the results that I have. But instead, let me give you a graphical representation of the main results. And let's start by plotting the carbon tax. So this, again, is a global model. So my calibration strategy is for this set of experiments that I show you here, I fix the parameter of the damage function. So in particular, I use a paper by Lind Barrage from 2013 and fix the damage function, or use her damage function. And then I vary the utility cost. Again, you could also fix the other and have variation in the damage function. But just to see how the results change for different damages or different climate impacts. So I plot the carbon tax. On the y-axis, you have dollars per ton of carbon. And on the x-axis, you have time. The blue line here is what would come out of the first best model. So I should mention, when I say first best, I basically mean the model with lump sum taxes. So if a government has access to lump sum taxes. The green line here is my optimal carbon tax without commitment. So yeah, I call it the Markov perfect outcome, basically. And then the red line in between would be the corresponding Pigouvian level, or in other words, the level of marginal climate impacts. And then the difference between the green and the red is what we can call the tax interaction effect. There's a slight, you can maybe say, misuse of terminology here. So what I call the tax interaction effect is basically what Larry Goulder called the tax interaction effect, but net off the revenue recycling effect. So this is kind of the two combined, and I still call it a tax interaction effect. And then this other, the shift from the first best outcome to the Pigouvian level is what I call in the paper a level distortion effect. So that just comes from the fact that having distortionary income taxes reduces economic activity, which reduces output consumption. But since the cost of climate change basically depends on output consumption, having distortionary taxes also leads to lower cost of climate change. So this would explain the shift from the blue to the red line. In this is the same picture. What I add here is this purple line, which basically gives you the corresponding outcome if we assume commitment, or if we assume that the government had access to a commitment device. And what's interesting here is that the green and the purple line are basically almost identical. So basically in this particular setting, it doesn't really matter if the government has access to a commitment device or not, in terms of when you're interested what the optimal carbon tax is. And we'll talk a bit about the intuition in a moment. So this was the case with high utility cost. Now I reduced the utility cost of climate change somewhat. And this is basically my baseline calibration, which corresponds to DICE, or which tries to replicate the temperature in DICE, or temperature change in DICE. So what you can see here now is that, of course, the scale on the y-axis changes. So climate change is less costly. The absolute level here is lower than before. But in terms of relative effects, the main thing that happens here is that the green line basically shifts up. So now there's a considerable difference between the optimal carbon tax without commitment and the carbon tax with commitment. At the same time, the tax interaction effect, which is given by the difference between the green and the red line, is almost zero in that setting. And then if we have even lower utility cost, the same, or we get an effect in the same direction. So the green line moves up even further, and it's now actually above the Pigouvian level. So in that sense, you would tax carbon above the Pigouvian level. Yeah. So main takeaways, to kind of summarize that, you could say the lower the cost, either the utility cost and or the productivity damages of climate change, the smaller is the gap between your Markov perfect carbon tax and the first best rate, but the larger is the gap between Markov perfect and the commitment outcome. And from a kind of more modeler's perspective, why that matters might be that if you want to kind of approximate the no commitment solution, so as I said before, without commitment, the model is much harder to solve numerically. So one could say that let's approximate it by assuming commitment. This is a better approximation the higher the cost of climate change are. And so, for example, Lind Barrage, the paper that I mentioned, this is a paper where she assumes commitment. In terms of interpretation, so this is kind of the main message of at least the first part of the paper, tried to condense in one slide, which was a bit of a challenge. So I don't want to go into too much detail. As I said, I invite you to read the paper. The tax interaction effect was already mentioned. So in my paper, there is a tax interaction effect whenever your optimal carbon tax is not at the Pigouvian level. And quantitatively, what I can see is that, let's take low damages, the optimal carbon tax exceeds the Pigouvian level. And this is actually different for the no commitment case, which is here given by the green line, and the commitment case. So what I plot here is basically the proportional deviation of the optimal tax from the corresponding Pigouvian level. So for first best, at first best we are at the Pigouvian level, so the deviation is 0. For the no commitment case, we have a higher tax, so there's a positive deviation, while for commitment, for commitment there's a negative deviation. And so this shows you that there is a difference between, conceptual difference, whether we have commitment or no commitment in these models. Okay. Then let me go to the two-region model. So think of this of a thought experiment. So what I do here is kind of a first step to having a more realistic model. So basically take the global model in the first part and divide it into equally sized regions. And then I assume that only one of those regions sets or has a carbon policy or chooses a carbon price and does that optimally. So this is an optimal unilateral policy if you want. And then I use somewhat of a trick here. I assume that the rest of the world is myopic. What that does is shutting down strategic interactions between regions, which some of you might argue, and a lot of people have argued, that that would be very interesting. And of course, I agree. The problem here is, of course, I have already a game in this model between successive governments, as I said before. So in order to keep it somewhat simple, I want to avoid having a second dimension of a game, in that case then between countries. I should also add, this is something I try to work or to do at the moment. So this is, in a sense, still work in progress. And what are my questions here? So first, again, asking in terms of the tax interaction effect, do we observe a similar tax interaction effect as in the global model? Then just maybe even more interesting, how large is actually the impact of distortionary taxation on emissions? And then also how much does capital mobility matter? So here I've plotted now emissions, so these global CO2 emissions per year over time. There's slight inconsistency with respect to the colors. So now the green line gives you the first best, or the global planner. So this would be global emissions if we had not only a lump sum tax, but also a global planner. And then the blue line would give you what would be the outcome under unilateral policy making, still assuming that there is a lump sum tax. If we have a distortionary income tax instead, the emission level would be somewhere in between. And this is partly, again, due to this, what I said before, distortionary effect, a reduction in economic activity, And since fossil fuel is complementary to labor and capital, there's also less fossil fuel used. At the same time, which I haven't shown here, there's also a tax interaction effect, which somewhat shifts this red curve upwards. So without the tax interaction effect, these emissions would be even lower. So this would be with capital mobility. Adding or abstracting from capital mobility, I get slightly lower emissions over time. Okay, before I give an intuition, let's go to the regional emissions. So this is just the same graph, but now divided in regions. So the green line is the rest of the world, which does not have a climate policy or carbon price. And then in the red one there is, in the purple one there is not. So that's it, sorry. Yeah. So this again is the case with capital mobility. So of course, since there's no climate policy in the rest of the world, they emit more than the domestic economy. If we abstract, if we take away capital mobility, emissions are somewhat lower in the domestic country, and in the long run also a bit lower in the rest of the world. And the intuition here is, of course, if there's capital mobility, this somewhat puts a bound on capital taxes. On carbon taxes, on capital taxes as well, but on carbon taxes. So the domestic economy could not impose, or would have to impose a lower carbon price compared to a non-capital mobility case. And then there is some, when you have capital mobility, there's some reallocation of capital from the domestic economy to the rest of the world. So in the long run, in the rest of the world, there's more capital, so they can also produce more and then emit more when you compare the green to the purple line. I already mentioned this. So yeah, just in terms of numbers and that, so this would be the baseline calibration. Tax interaction effect here would tell you that the Markov perfect carbon tax is approximately 20% lower than the Pigouvian rate. And yeah, again, the intuition, with capital mobility, the domestic region would have to reduce the carbon tax and the rest of the world would experience more capital imports. And then, as I said, this is still a bit work in progress. So what especially I want to do, I want to get a better calibration of the model and maybe also put it in terms of EU versus the rest of the world. And I would try to implement a proper game between regions. But if anyone else has suggestions, I'd be very happy to listen to that. Thank you.